Let's look at some different data. It also consists of a signal plus some random noise. This time, part of the signal that I've created is a straight line, and it's much bigger than in the previous example, so that this time, part of the signal at least is kind of obvious when you look at the data. I do want you to test things, though, statistically. There are times when we see something that looks like it's totally obvious, couldn't possibly be denied, but when you test it, it doesn't pass muster. There are also a lot of times when you can't really see anything to the eye. It doesn't look like there's anything going on, but when you do some tests, you find something that is real. In this case, I have actually tested for the straight line part of the signal, and yes, it's real. You can see it pretty plainly here, and it's a big enough slope compared to the noise level that the signal to noise ratio is big enough to make the trend kind of obvious. The million-dollar question, of course, is what else is there signal-wise? Is there anything there other than just noise? Well, we could go looking for more signal by trying a bunch of models like we did before. We could try stepwise regression with polynomials or other kinds of stepwise regression. But I'd like to get into something a little bit different that helps us look for signal amongst the noise. I'd like to introduce the idea of smoothing data. When data consists of signal plus noise, the noise kind of hides the patterns that exist in the signal and make them harder to detect. In such cases, in the cases we've looked at, the noise is quite big compared to the signal, especially except for that linear trend in the last data. So instead of looking for more pattern with lots of models, let's suppose we could increase the signal to noise ratio by reducing the noise without much interfering with the signal. Well, one way to do that is to go about smoothing the data. There are lots of ways to smooth data. I've said on occasion, and I was only half joking, that there are as many smoothing methods as there are analysts who use them. We're going to start with the simplest way to reduce the noise, just averaging. We're going to take the time span of data, chop it into slices. Then we'll compute the average value within each slice and assign that to the average time during the slice. What averaging does is it reduces the noise, and it usually creates very little interference with the part of the signal which unfolds on slow timescales. A danger is that averaging can greatly interfere with signal which unfolds on fast timescales. In fact, if the length of time over which you average is longer than the time scale of the signal, you're going to make that signal disappear. But we're going to go looking for a slower, more long time scale signal to see what's going on. And in that case, we can apply averaging, and we're not going to worry at the moment about interfering with the signal. We're just going to rely on them to reduce the noise. Now, the data we've been looking at are meant to simulate monthly data. There are 12 values each year. Let's transform them into annual averages just by computing an average every year. We slice the times of observation into years and compute an average within each year, and then they are plotted as the red dots. You can see that they seem to follow a straight line with a bunch of wiggling around. The original data had a bunch of wiggling around because it had noise in it. Well, when you average noise, you're going to get noise. So the averages, the one-year averages, will also have noise. They'll have the signal too. The thing is, the signal has not really been changed, but the noise has been greatly reduced and therefore made a bit clearer. Now, these are averages over every 1 year. We could average over longer time spans. For instance, we could average over every 5 years. We could average over every 10 years. We could average over every 20 years. We can actually divide the time into slices as big as we want. Here are averages over every 5-year time slice. Now we can see that the smoothed values, the red dots, they're still roughly following a straight line plus wiggling around because they've got noise. But there's far less wiggling around. There's far less noise. We've eliminated most of the noise without interfering with the signal, and we're getting a better idea of what the data are telling us, at least on longer time scales. When we go to 10-year averages, we're extremely close to having just a straight line, plus a little bit of wiggling around that is greatly reduced. If we go to 20-year averages, we get so little noise that it almost looks like a perfect straight line. And we have accomplished the goal of our smoothing simply by computing averages. We have kept the signal intact, but we have greatly reduced the noise. Now, all those smooths, they seem to follow the simple straight line that we fit to the data to begin with. There's another advantage in computing averages, and that is we can compute the uncertainty of the average itself. It's the standard statistical formula for the uncertainty of an average. Let's compute those 20-year averages and their uncertainties and use those uncertainties to plot error bars, 95% confidence error bars. Then let's plot the averages with their error bars and compare that to the linear regression fit we got at the start. We see that the linear regression fit, the straight line model, falls within the error range for each 20-year average in every case. Even when the model is exactly correct, it won't be the case all the time, because let's face it, an error bar, which is a 95% confidence error bar, is not going to include the true value about 5% of the time. But in this particular case, it does in every one of the averaging intervals. That's pretty good confirmation that so far our evidence is strongly pointing to a straight line signal plus random noise. Now the averages, they don't just significantly depart from our originally fit, so that's a sign that the linear fit might be right, maybe. It's certainly a good approximation. There is, however, a complication to what we are doing with computing averages. When we divided time into slices, we just divided them at each multiple of 20 years. So the first one was from time -60 to -40, although there wasn't anything before -50. The next one was from -40 to -20, then from -20 to 0, then from 0 to 20, etc., etc., etc. Why those boundaries? Why couldn't we have used boundaries to divide it into slices from -50 to -30, and then from -30 to -10, etc., etc., etc.? Well, the fact is we could have. We could have chosen anywhere we want to be the moment between different segments of time. As a matter of fact, we could have computed an average of a given length over any boundary that is that long. What if we computed averages over every possible window of the requisite length? Now that'd be a lot more averages to compute. But it would give us something that is very useful. It's called moving averages. The first averages is from time t1 to tn, where n is the number of time points in the averaging window. So it's the first n data points. Note that for a 24-year average of monthly data, there are 240 points per average. So the very first average is for the first 240 data points. This average value is taken as the smoothed value at the average time in the window. The next one, we advance the window by one data point. So the next average will be on data points 2 through 241, and it applies to the average time of that window. And we keep advancing the window by one data point at a time and end up generating a lot of average values. The final average is just the final 240 points of the observed data if we're doing a 240-point moving average. Something to notice is the very first average is the data from 1 to 240. The very next average is data points 2 to 241. Each one of those is an average over 240 data points, but they have 239 out of 240 data points in common. There's a great deal of overlap between nearby windows in moving averages. The smoothed value is the sum of certain weights times the data point values. Now the weights are 1 over n, where n is however many data points we're putting in our moving average. It's how wide the window is. And the window, the weights themselves kind of slide through time, advancing one data point at a time. By the way, note that the weights have to add up to 1. The reason for that is that if the data are all equal to some constant, then we insist that the smoothed value has to equal that same constant. Now, we could plot this weight function, which is 1 over n, for however many data points go into a moving average. We could plot it for all time if we set the weight function to 0 outside the averaging window. And that makes it into a boxcar function. Now, the process of computing sums like that, weights times data values, and then sliding the weight function through time, it's the application of a filter to the data. The filter is the weight function. In this case, it's a boxcar function. Just as an aside, we can apply the idea of filtering to continuous data rather than observed and therefore necessarily discrete data. If we have a continuous function of time f of t and a filter w of t, then the smoothed or filtered result is given by this integral, and the process is usually called the convolution of the functions f and w. Well, when we apply a 12-point boxcar filter to our data, that's a 1-year boxcar filter or moving average, we get the red line shown in this graph. We can see that it still wiggles around quite a bit because, let's face it, there's noise going into the filter, so there's going to be noise coming out. But the signal is unchanged. The noise, however, is reduced. We don't have to restrict ourselves to a 1-year or 12-point boxcar filter. We could go with a 5-year boxcar filter. Now the noise is reduced even further. In fact, it's starting to look closer to a straight line. There's still a good bit of wiggling around, but the wiggling around due to noise is greatly reduced. We can go from a 5-year or 60-point boxcar filter to a 10-year or 120-point boxcar filter. Now we're getting quite close to a straight line signal coming out because the noise has been so greatly reduced. We can even go up to a 20-year or 240-point boxcar filter, and now the smooth values shown by the red line really strongly resemble a straight line. So it really accomplishes the goal we set out to in the first place, which is to leave the signal unchanged, but to reduce the noise greatly. I will remind you that if there were genuine signal here that operated on a fast timescale, say an annual cycle, well, a 20-year boxcar filter is going to smooth out that annual signal. So filters, the longer their timescale, the more they tend to eradicate signal that is of a fast timescale. In this case, that's not going on, so the filter is safe. It doesn't alter the signal at all, but it greatly reduces the noise. Another thing to be aware of is that for a boxcar filter to work right, it has to include the entire window has to include observed data. That means that for a 20-year filter, its midpoint has to be 10 years from the start or end of the observed data. That means that when we compute our filtered values, we're going to lose 10 years of time at the beginning. We're going to lose 10 years of time at the end. Essentially, we're going to lose half a filter width at both edges of the data.